All right, ladies and gentlemen, welcome back. In the last lesson, one of the things that we talked about as far as functions were concerned was how to identify the domain of a function either by looking at a graph or by looking at maybe a table or something like that. Well, one of the things that we're going to be talking about now is how do you identify the domain of a function or the domain of a type of function from an equation. Now, for most of these, it's not an issue. Let's see, come here, pen. Why aren't you working? There we go. For linear equations or functions, quadratic, really just about any polynomial, meaning like something x to the first, x to the second, x to the third, x to the fourth, etc. For really any polynomial and even absolute value, the domain would be anything, everything. The domain would be all real numbers. But there are a couple, or there are a few functions that do not have a domain of all real numbers. We have certain, well, like a logarithmic function. We might have radical functions, and we might have rational functions, and there might be a rational, there might be more, but I'm just not able to think of them off the top of my head right now. Uh, Most types of functions slash equations have a domain of all real numbers. Not all of them, however, and these are three examples. Now, out of these three that do not have a domain of all real numbers, we're particularly going to be looking at radical and rational equations because those are the ones that we're most familiar with right now. Logarithmic equations and functions we'll get to later on. Okay, so pardon me. If your function is a rational function, the thing that causes it to not be allowing to, or that causes it to not have a domain of all real numbers is if I have a number that would produce a zero in the denominator. If I have something like, say, y is equal to 1 over x, x could not be 0 because we can't have 0 in the denominator. So we could say that the domain would be everything except for 0. So anytime I have a rational function or a rational equation, I really need to see, okay, well, what would make a 0 in the denominator? And that's kind of what we're going to take a look at first. So here we have two functions, two equations, however you want to think of it. And basically we want to see, okay, well, what could create a 0 in the denominator? So all I'm going to really be concerned with at this time is what is in the denominator. So I'm going to say, take the denominator and set it equal to 0, and then solve for x. So move the 3 over, and in this case, x would equal a negative 3. Well, in this case, kind of what we're thinking of, it might be easier to think of it as that this is what x cannot equal. So in this case, x cannot equal 3, because if I put the negative 3 back into the denominator, that would give me a 0 there, which would make the equation or the function undefined. So 3 is the only number for this first example that cannot be part of the domain. Now there's two ways that we could kind of write it. We could say set notation. How could I express my answer in set notation? Well, set notation again uses the curly brackets, so I would say x such that x simply cannot be negative 3. That's how I would write my answer in set notation. In interval notation, and I'm showing you both because we're not actually being asked to specify, but if we do say set notation or interval notation, you'll know which way to do it. So interval notation says I can be anything except for that negative 3. So I can be all the way from negative infinity up to, but not including, the negative 3. and I can be from -3 all the way up to positive infinity. And since we're kind of saying, well, we can't do the -3, we have to have that break there. That's what the parentheses are doing, rather than using a bracket. And since we do have the break, we want to include both sets of the interval with the union symbol. Excuse me, I'm sorry, I have a frog in my throat. So now let's take a look at the second one. And again, this is a rational equation, or a rational function, because it has a variable in the denominator. That's what makes it rational. And all I want to do is look at the bottom, see what numbers could I not use in the bottom here, because we can't have something that'll make 0. So if we work this out, move the 49 over, I'm going to get x squared to be a positive 49. And if I take the square root of both sides, I'm going to show that x could not be a positive or a -7. Because if I put either of those two numbers into the denominator, that would give me a 0. So those are the two numbers that we could not use here. So let's show it in set notation. Here it's actually a little easier to write it in set notation. I'm going to say x such that x cannot be positive or -7. In interval notation, well, we can go from -infinity all the way up to, but not including, a -7. And from -7, we can go up to a +7. And then from a +7, we could go all the way up to a positive infinity. So you see how sometimes the set notation would be a little bit more friendly to show what the domain would be rather than interval notation. So that is pretty much how we're going to look at for rational equations. We want to see what would make the bottom 0, and then those are the numbers that we can't use. So now let's take a look at radical equations or radical functions, either way you want to kind of think of it. Now, mathematically speaking, we cannot have real numbers, which is what the domain is made of, real numbers. We can't have real numbers that will produce a negative underneath a radical. So let's just say, for instance, if I said the square root of let's say 3 minus 1. Well, that would give me the square root of 2, and that's a real number, so we could use it. But if we turn it around and said 1 minus 3, that would give me a negative 2, which would give me an imaginary number. So imaginary numbers aren't real, so they cannot be part of a domain. So anything that will give you a negative number underneath the square root symbol can't be used. So because we can't use it, instead of setting it equal to 0 like we did for a rational equation, we're going to take whatever is underneath it, underneath the radical, and set it greater than or equal to 0, and then solve it. So let's take a look at a couple of these. Here I have two functions, f of x is equal to the square root of 2x plus 3, and negative 2x plus 6. The stuff underneath the radical symbol is called a radicand. What it told us to do is to take the radicand and set it to where it is greater than or equal to 0. And now let's solve for x. So if I move the 3 over, I'm going to get 2x to be greater than or equal to negative 3. Divide both sides by 2, and I would say x must be greater than or equal to negative 3 over 2. So I could have negative 3 over 2, which would give me a 0. I could take the square root of 0, and that's fine. But anything that would be smaller than that would give me a negative number from my radicand and would therefore not be part of the domain. So how would I write the domain for this? Let's again look at it in set and interval notation. Set notation is going to be pretty easy to do here. Again, we'll just say x such that x must be greater than or equal to negative 3 over 2. And in interval notation, this one's easier to do because we're only looking at a certain set of numbers. So x has to be everything that is 3 over 2 negative and bigger. So we are going to say it can actually be the negative 3 over 2, so we'll use the bracket 3 over 2, and it can go all the way up to positive infinity. So that's how we would write that one in interval notation. And let's take a look at our second one. So just like what we did with the first one, take the radicand, make it greater than or equal to 0, and then solve for x. So if I move the 6 over, I'm going to say negative 2x to be greater than or equal to negative 6. Now here, we have to pay attention to what we're doing with our inequality symbol. Since I'm dividing with a negative number, I have to turn the inequality symbol around. And so I'm going to say now x has to be less than or equal to positive 3. So everything that is 3 or less can't be part of the domain, because that would give us an a negative number as a radicand, which would create an imaginary number. So imaginary numbers are not going to be part of a domain. So set notation here, we would say x such that x has to be less than or equal to positive 3. And in interval notation, well, since we can use everything less than 3 all the way up to it, we'd say from negative infinity up to 3, and we can use the 3, so we put the bracket around. And that's pretty much it as far as identifying what the domains would be for a rational or a radical equation. Now let's take a look at a combination. These are going to be slightly more complicated, not a lot more complicated, but slightly more complicated, because it's going to take the concept of both a rational equation and a radical equation and kind of combine them together. So make sure you kind of read this over, write it down into your notes if you feel it's going to be stuff that you need. But I think let's just go ahead and look at the practice problems here. Now, here, this is a radical equation in the form of a rational equation as well, because the radical comes from the fact that we have the square root symbol, and the rational meaning that the variable is in the bottom of the fraction. So looking at it this way, looking at just the bottom part, okay, we would say that here x plus 3 has to be greater than, I'm sorry, not greater, cannot be equal to 0. And if we look at the entire expression, the 7 over the x plus 3, all of that has to be greater than or equal to 0. So both of these conditions have to be met. So here on the right side, because x cannot be equal to 0, we must therefore now kind of take this part away, because this says it could equal 0, but this says it can equal 0. So since they contradict each other, the negative wins in this case. We cannot use 0 at all. So the final thing is going to be that x plus 3 can be greater than 0, but not greater than or equal to 0. So now we just solve for x, and so here I'm going to say x is greater than 3, and that tells you what the domain restrictions are, or what will actually be in the domain. So in set notation, I'm going to say x such that x is greater than 3. And in interval notation, I would say from 3 to positive infinity. And I use the parenthesis on the 3 because we can't actually be the 3. We have to be greater than the 3. And for the last example that we have here, we have, again, kind of a combination. We have the variable in the bottom, again, but in the bottom, the entire denominator is a radical expression. So the denominator itself, the 4x plus 5, that whole thing can't equal 0. But the radicand itself, the 4x plus 5, must also be greater than or equal to 0. Well, same thing like in the last one, because this one says it can't be 0, and the one on the right says it could be 0. Because they contradict each other, we have to, err on the side of caution and say, well, we can't have 0. So I'm going to simply take the 4x plus 5 and say it must be greater than 0, and now solve for that. So move the 5 over, and I get 4x to be greater than negative 5, so x is greater than negative 5 over 4. And again, to write it out in set notation, we would simply say, curly bracket, x such that x must be greater than negative 5 over 4. And in set notation, we would say from negative 5 over 4 up to positive infinity. And that's pretty much what we're going to be taking a look at for how we determine the domain of an equation. Again, there are other equations that will not use all real numbers, but we'll save those for a little later on. Right now we're going to just focus on rational and radical, and that's how you do those two. So if you have any questions, again, please make sure you come see me, and see you in class soon. Thanks.